Welcome to The Explainer. Today, we're diving into something absolutely crucial for anyone staring down the barrel of a highly competitive physics exam. We're going to start broad, looking at high-level prep strategies, and then we'll zoom way into the nitty-gritty of wave optics. So it's going to be this really fun ride from the theoretical all the way to the intensely practical. But first, let me ask you something. What does it actually take to conquer the world's most competitive exams? I mean, we're talking about the absolute monsters of the Indian competitive exam circuit here. If you picture yourself as the hero of this story, standing at the base of a massive mountain, well, before you start climbing, you need to gather your weapons, right? You've got to understand the terrain and learn the cheat codes, and that is exactly what we're breaking down today.
Okay, here is our roadmap for today. First, we'll look at the exam landscape, then we'll unpack the physics toolkit. Third, we'll focus on optics. Fourth, cracking wave optics, and finally, number 5, the ultimate strategy. Let's get into it.
Section 1. The exam landscape. Understanding the scope of the challenge.
I mean, just look at the massive scale of the exams we're covering. We've got the joint entrance examinations, JEE Main and Advanced, the medical heavyweights like NEET and AIMS, and the graduate aptitude test in engineering, or GATE, across a bunch of different disciplines. Plus, there are the massive state-level exams like WBJE and MHTCET, and even the civil services exam under the UPSC. The stakes here, they're astronomically high. But here's the silver lining. While these exams lead to wildly different careers, the universal language you need to beat them is, you guessed it, physics.
Now, when we actually look at the physics syllabus across all these tests, it kind of neatly divides into two main camps. Over on one side, we have the foundations, right? Mechanics and electricity. This is where you learn the basic rules of the universe, motion, forces, fields. But then on the other side, we have the applications, like optics and modern physics. And this is where things get a bit more abstract and heavily application-based. To actually succeed, you have to master both that solid bedrock and its complex applications.
Moving on to Section 2, the physics toolkit, mastering the foundational formulas.
So, if you're the hero going into battle, these formulas are literally your essential weapons. Comprehensive formula guides, like the ones from platforms such as Testbook, act as your ultimate playbook. You absolutely cannot walk into these exams trying to derive every single equation from scratch. You just don't have the time. You need these mathematical tools sharp, memorized, and ready to deploy at a moment's notice. But before things get too crazy, we have to ground ourselves in the absolute basics, like Cartesian vectors. Take the resultant vector formula. It shows us exactly how to combine two forces, or, say, two waves, based entirely on the angle between them. Whether you're dealing with pushes and pulls in mechanics, or the superposition of light waves in optics, understanding how vectors interact is just non-negotiable.
Then, of course, we have projectile motion. Notice how the formulas for maximum height and horizontal range heavily rely on two things: the launch angle and the initial velocity. But the real trick here isn't just mindlessly memorizing the equations. It's about visualizing them, realizing that horizontal range is always maximized at a 45-degree angle. It's about actually seeing the physics, not just staring at the math.
And before we pivot, just look at how the math scales up when we get to rotational motion and center of mass. Instead of simple mass, suddenly we're dealing with moment of inertia, which changes totally depending on whether you're looking at a rod or a disk. Like, a rod at the center is ml squared over 12, but a disk is mr squared over 2. The complexity ramps up really quickly, which is exactly why having that core toolkit completely locked down is so vital.
That brings us to Section 3, focus on optics, the battleground of previous year questions. Optics is deeply fascinating because it literally forces you to think about light in two completely different ways. On the one hand, you have geometrical optics. That deals with physical shapes, lenses, prisms, mirrors, focal lengths. Light is just treated as a simple, straight ray. But on the flip side, we have wave optics, and this is where we deal with light's fundamental wavy behavior. Stuff like interference, diffraction, phase differences, and that famous Young's double slit experiment. This is where the concepts get really fun.
Section 4, cracking wave optics, unlocking the Suvajit Academy transcript. All right. This right here illustrates the core mathematical key to wave optics, the net intensity formula. Notice how it doesn't just simple math add two light intensities together. Instead, it factors in the exact phase difference between them. And honestly, the best part? If the two interacting waves happen to be identical, this massive, clunky equation elegantly simplifies down to a much shorter, highly manageable formula. You master this relationship, and you've basically unlocked a huge chunk of the exam.
Now, exam centers absolutely love to test your speed, which is why recognizing the maximum and minimum intensity ratio is a massive cheat code for previous year questions, or PYQs. As the instructor from our source points out, spotting this specific ratio trick lets you bypass entire pages of tedious algebra and jump straight to the correct answer. It is a real game changer.
So if we break down the instructor's approach to conquering those really daunting interference problems, it becomes a highly structured, repeatable algorithm. Step 1, immediately identify the phase difference or path difference. Step 2, apply the net intensity formula based on that specific phase. And step 3, if they ask for ratios, jump straight to calculating the max/min intensity ratio. Boom, 3 simple steps to a solution.
Okay, let's talk about fringe width, represented by the Greek letter beta. This simply represents the physical distance between consecutive bright or dark fringes on the viewing screen. But the absolute key takeaway you need to remember here is that fringe width is directly proportional to the wavelength of the light being used. If the wavelength changes, that entire fringe width changes right along with it.
Which actually leads us to a highly specific and, honestly, kind of surprising scenario that pops up all the time in exams like WBJE, the liquid immersion rule. Think about it. What happens if you take the entire double-slit experiment and submerge the whole shebang in water? Well, because the liquid's refractive index alters the light's wavelength, the new fringe width simply becomes the old fringe width divided by that refractive index. It literally shrinks proportionally. Knowing this little shortcut is going to save you from doing a massive, complex derivation right in the middle of a high-stress exam.
Finally, to cap off our wave optics deep dive, we have to briefly touch on Fraunhofer diffraction. This is a very specific diffraction pattern that, theoretically speaking, only occurs when the light source is at an infinite distance away, which creates perfectly parallel incident beams. The source transcript emphasizes that understanding these strict, theoretical requirements is just as important as the practical math, mostly because exam setters love to test you on these tricky conceptual boundaries.
Let's bring it home with Section 5, the ultimate strategy, how to actually win the exam. I want you to read this quote directly from the educator in our source transcript. When a student asked for a magic resource with only a couple of weeks left before the test, the instructor replied with this absolute urgent passion. Mock test, analyze mock tests. Where did you go wrong? Solve every question from the mock tests. That is the mock test analysis. Listen, there is no secret book. The only true path to success here is relentlessly practicing previous year questions and totally tearing apart your mock tests to see exactly where your understanding failed.
So let's summarize all these actionable takeaways into a quick winning playbook. First, dedicate your time strictly to previous year questions. They are literally the blueprint of the enemy. Second, take standard mock tests repeatedly and under timed conditions. Third, and I cannot stress this enough, analyze every single error after the test. Let it take all day or all night if it has to. Fourth, keep that formula toolkit completely memorized. And finally, do not just read the physics, you have to actively solve it.
Well, we've gone from the broadest exam landscape all the way down to the highly specific intensity ratios of wave optics. We've laid out the tools, we've laid out the strategy, so my final question to you is this. Are you ready to turn these formulas into your ultimate exam strategy? Stop waiting around. Grab a pen, pull up a mock test, and start solving. Thank you so much for joining me on this explainer. Until next time, keep learning, keep analyzing, and go conquer that exam.